Okay, hello, my name's Chris, and today I'll be speaking to you about explainable anomaly detection. Just a note up front that the level of today's talk will be introductory, but it will be somewhat technical, and I just want to make sure that everyone feels encouraged to stick around and ask questions, regardless of your comfort level with the technical details. And I will try to focus on building intuition through simple examples and stay away from overly complicated details. Okay, so before we get started, let's go over what I have planned for the hour. I'll begin with an introduction to faculty, as well as my role at the company. Then I'll give some background on AI safety and how we pursue it at faculty. Then we'll get into the meat of today's talk on anomaly detection. And after that, we'll discuss explainability and how we think it should be done in the context of anomaly detection. And finally, I'll go through a simple demo on synthetic data, showing what can go wrong if explainability is not done correctly. And then at the end, I'll look through your questions and answer as many of them as I can. So feel free to post questions throughout the whole talk, but I will save those for the end, so I won't see them until the last 15 minutes or so. Okay, so let's start with the intro to faculty. Okay, so Faculty is an applied AI company founded about 5 years ago with the goal of making AI real, by which we mean making it accessible and impactful for anyone who would like to see how AI can transform their business. Despite being relatively young, we've worked on hundreds of very successful projects with leading companies around the world and in many different sectors of the economy. And at Faculty, we believe that making AI real is synonymous with making it safe. So Faculty has an R&D team that focuses on original research on the AI safety problems that are important to solve to make today's AI safer. And we've already made significant progress on this, for example, with somewhere around 12 research papers in the last 2 years. That's me in the middle. Again, my name's Chris. I'm a research scientist at Faculty, and I'm a primary contributor to Faculty's research on AI safety. I've got a background in theoretical physics, and I joined the R&D team at Faculty about 2 years ago. Since then, I've focused in particular on explainability and robustness. Those will be very relevant for today's talk. And I've also worked on privacy and fairness in machine learning as well. Okay, so next, let's talk about AI safety at Faculty. All right, generally when people think about AI safety, a variety of different specific concerns might come to mind. Some of these things, like political disinformation, are already becoming concerning today, whereas others, like existential risk, are farther off. And at Faculty, we structure these concerns along 2 axes. The horizontal axis is the intention of the technology's designer, with benign or even benevolent intentions on the left and malicious intentions on the right. The vertical axis is the autonomy level of the technology, with human controlled at the bottom and autonomous decision-making at the top. The vertical axis correlates with time. So present day AI is somewhere at the bottom, and more futuristic concerns like existential risk are at the top. And it's also worth noting that this is just meant to be a rough structure to organize our thinking around AI safety problems. Okay, so we can add one additional dimension to this chart as well, namely color. Certain specific AI risks will have technical solutions, and we've colored those in coral. Other problems will require thoughtful public policy, and those are in yellow. On the R&D team at Faculty, we focus primarily on solving the technical problems in the lower left quadrant of this chart. These are the AI safety problems that are relevant for AI that gets deployed today. And this is where our technical team can make the largest impact. And we break this lower left quadrant into 4 pillars of technical AI safety. These are explainability, robustness, privacy, and fairness. And for today's talk on explainable anomaly detection, the areas of explainability and robustness will be most relevant. Here, explainability focuses on how a model makes its decisions, whereas we think of anomaly detection as sitting under the umbrella of robustness. And that's because to ensure that a model will perform robustly, it's important to be able to sort of sound the alarm when it's fed anomalous inputs. All right, so let's get into the main part of today's material now on anomaly detection. Okay, so first, what is an anomaly? An anomaly is a rare observation that breaks the trends that are normally satisfied by the data. Anomalies often arise out of a different data generating process than what's generating the majority of the data. For example, the typical data might correspond to, say, legal financial transactions, sort of business as usual, while the anomalous data corresponds, say, to criminal activity. And anomaly detection is, in its purest form, an unsupervised task. We're simply looking for events that do not follow the usual trends in a data set. And this is in contrast to a supervised task, like learning to classify data based on historical examples. So anomaly detection is quite different from that. And anomaly detection is important because of its many applications. At faculty, we got started on anomaly detection from the perspective of AI safety. In this context, being able to detect anomalous inputs to a model or even global shifts in the data distribution over time, these are very important for model monitoring. Anomaly detection basically is a tool that tells you when you should expect your model to break down in this context. Outside of AI safety, anomaly detection is important itself as a direct task. It's a technique used, for example, to detect financial crime, whether that be money laundering or fraudulent transactions. And it also has applications in other fields, for example, in medicine or for system health monitoring and many other things. In today's talk, though, I'm not going to focus on any one of these particular applications. Instead, I'll speak about technical anomaly detection more generally. Okay, so in general, there are two classes of anomalies. On the left, we have single feature anomalies. These are both easy to detect and easy to explain. They arise when an individual feature in your data takes an extreme value. For example, here's a histogram of the values that an individual feature takes across the data set. And on the far right, in this left-hand plot, beyond the tail of the distribution, we can see there are a couple of anomalous data points. And as the name suggests, single feature anomalies can be explained simply by plotting a histogram of the incriminating feature. In the plot on the right, we have what we call correlation anomalies. These are anomalies for which no single feature takes an extreme value, but instead the data point breaks correlations that are satisfied by the rest of the data. So for example, in what's shown here, neither feature 1 nor feature 2 takes an extreme value. But feature 1 is on the high side, while feature 2 is on the low side, and this never happens simultaneously in the rest of the data. Now, in this simple example, it's easy to see what's going on in 2 dimensions, but correlation anomalies really can't be visualized in realistic high-dimensional data, where a correlation might be broken between dozens of features. So both detection and explainability in this case is much more difficult. And an explanation, for example, should indicate which features are responsible for the anomalous behavior. Okay, so a couple slides ago, I said that anomaly detection is inherently an unsupervised task. So faculty's AI safety stack, that includes explainability, robustness, and privacy, for example, is all based around a powerful unsupervised technique, and that's the variational autoencoder, or VAE. So let's spend a minute understanding how VAEs work, because this will be relevant for anomaly detection. So the VAE is a neural network that's trained to reconstruct the input data that it's trained on. So for example, if we feed in these images of handwritten digits, the VAE will be able to reconstruct them. What makes this difficult is that there's an information bottleneck imposed in the middle of the VAE. This forces the VAE to encode each high dimensional input data point into a low dimensional representation at the information bottleneck layer. And the low dimensional representation must contain all the necessary information to reconstruct that input data point. The VAE is able to pare down its representation by basically removing redundant information. And in order to do this, the VAE learns the complex correlations that exist in the data. So the fact that the VAE learns the correlations of the data set is already a hint that VAEs might be useful for detecting correlation anomalies. And let's understand how this might work. So imagine the VAE is trained to reconstruct these handwritten digits. In particular, let's say that 99% of the VAE's training data consists of just ones and zeros. And let's consider the remaining 1% of the data consisting of the other digits to be anomalies. So in this case, the VAE will learn to reconstruct ones and zeros very well, but the way it represents the data in the information bottleneck layer won't be quite right for reconstructing the other digits that it only saw infrequently during training. That means that the reconstruction accuracy can actually be used to detect anomalies. When reconstruction accuracy is high for the ones and zeros, that's an indication that this data point is not anomalous. Whereas when reconstruction accuracy is low, like for the rest of the digits, that's an indication that this is an anomaly. So this shows one way that the VAE could be useful for anomaly detection. Let's talk about where this VAE-based approach sits first, though, in the context of other methods for anomaly detection. So methods for anomaly detection can be thought of on a spectrum from shallow to deep. At the shallow end of the spectrum are classical methods that have been around for a decade or two at this point. This includes, for example, isolation forests and one-class SVM. On the deep end are direct deep learning methods. This would include the reconstruction accuracy of the VAE that we just discussed. There are also, for example, GAN-based approaches here as well. And in fact, in the middle of the spectrum, there are mixed methods too. In a mixed method, deep learning is used to extract a low dimensional set of features from the raw data. And then these extracted features are then fed to a classical method to actually perform the anomaly detection. So sort of, you start with high dimensional data, you process it with a deep learning method to extract a low dimensional set of features, and then you pass these low dimensional features to the classical method, like an isolation forest, for example, to actually do the detection. Okay, and in fact, we found in our own experiments that using the VAE in a mixed approach actually achieves the best anomaly detection performance. So the way this works is that for each data point, we actually extract several features from the VAE. On the slide, these extracted features are shown as reconstruction accuracy and the KL divergence, but in reality, there are about 10 of them in all that we extract. And then we pass these extracted features to an anomaly detection method, a classical method, for example, an isolation forest. And we find that extracting multiple features from the VAE like this allows us to perform better than just using a single feature, like the reconstruction accuracy by itself. Okay, so that's how faculty does anomaly detection. And let's talk for a minute about how we judge the performance of an anomaly detection algorithm. So what we actually get as output from an algorithm is the anomaly score for each data point in the data set. And it's supposed to be the case that large scores are assigned to the anomalies and small scores are assigned to the non-anomalous data. So here on the left, let's say that we have a histogram of all these anomaly scores, where I've colored the true anomalies in coral and the truly non-anomalous data in gray. To actually make a prediction here, we need to choose a threshold. So let's say we put the threshold at 0.3. Above that threshold, we would predict that all the data is anomalous. And below that threshold, we wouldn't detect any anomalies. So you can see from the plot then that above the threshold, there will be both true positives and false positives. And below the threshold, there will be true negatives and false negatives. So this threshold won't lead to perfect anomaly prediction. But we can use these quantities, the TP, FP, TN, and FN, to create a few different performance metrics that I've listed on the right. The most obvious one is accuracy. This is just the number of correct predictions, meaning the true negatives and the true positives, divided by the total number of predictions altogether. So total number of data points in the denominator. But accuracy is actually not such a useful metric, it turns out, for anomaly detection. That's because anomalies are rare. For example, if the data only contains 1% anomalies, then you can get 99% accuracy without actually detecting a single anomaly. So accuracy can often be misleading. There are a couple other metrics that are more useful in this context of heavily imbalanced classes. These two metrics are precision and recall. So precision is the fraction of all predicted anomalies that are truly anomalous. And recall is the fraction of all true anomalies that are actually detected. And when I say these two things in English, these quantities sound almost identical, but the difference mathematically is that precision is sensitive to false positives, whereas recall tracks false negatives. So anyway, the takeaway from this slide is that precision and recall are two performance metrics that we use to judge algorithms, and the higher the better for these performance metrics. All right, so now that we've discussed performance metrics, let me show you the results of some benchmarking experiments that we've performed to compare faculty's approach to anomaly detection against what's available in the open source. So each vertical stack of points here in this plot corresponds to a different data set or use case. We've tested each method, for example, on MNIST, on a credit card fraud data set, and on a network intrusion data set. And the height of each point corresponds to that particular method's precision on the given data set. So faculty's method is in coral, and the open source methods are in varying shades of gray. And just to be a little bit more precise, that's actually the precision averaged over all values of the recall. So what you can see from these experiments, though, is that our method is the only one that shows consistent top performance across data sets and use cases. The best performing open source alternative just varies from experiment to experiment and from data set to data set. And here's a simplified version of those results from the previous slide, sort of an aggregation of these experimental results. So what we're showing here is that faculty's average performance across all the data sets and use cases. That's in coral. And different coral points here just correspond to repeated experiments to give you a sense of the consistency of our performance. And in gray, we compare to the leading open source algorithm on each data set and use case. So even though the leading alternative varied with each experiment on the previous slide, the gray points just represent the top performing open source method on that particular experiment. And the different gray points, again, correspond to different repeated experiments. So a couple slides ago, I said that the precision metric that we're plotting here on the vertical axis is sensitive to false positives. So what the result on this slide means then is that faculty's approach to anomaly detection leads on average to a 16% reduction in false positives. And our approach also leads to about a 50% smaller spread in performance than the open source techniques. So just to summarize then, faculty's method leads to a significantly reduced false positive rate, as well as substantially more consistent and robust performance. Okay, so now let's move on to explainability for anomaly detection. So explainability plays an especially critical role in automated anomaly detection. And in fact, it's important for pretty much everyone that's involved with the model. For example, explainability can be important for meeting regulatory requirements. It can be used by developers to understand model performance and to understand failure modes in order to make iterative improvements to the model. And perhaps most importantly, in the context of anomaly detection, good explainability can expedite the false positive triage process by pointing human investigators in the right direction as they check whether a particular event was truly anomalous. Okay, and if you've heard of it, the Shapley framework provides a great starting point for principled model explainability. This is because Shapley values are founded on an intuitive set of mathematical axioms. And on the right is an example of what Shapley values look like in practice. They can be visualized in a bar chart, for example, and they assign a level of importance to each of the model's input features. And in a little more detail, Shapley values basically answer the question, what portion of a model's prediction is due to each input feature? So Shapley values answer this question in a particular way. Take this example of a model that has 3 input features, x1 or x0, x1, and x2. So in order to determine, for example, the importance of feature x1 towards the model's prediction of y, a Shapley calculation would involve withholding x1 as an input and measuring the effect this has on the model's prediction. Now, right away, this forces us to ask the question, though, what does this empty input slot mean? Of course, the model's output can only be evaluated if all the input slots are filled. So what this really means is that we should compute the model output averaged over all the possible input values for x1. And what we'll see over the remainder of the talk is that the way this average is performed is crucial for getting correct explanations. Okay, so now it turns out that the open source methods for explainability actually fill in this empty feature slot with unrealistic values that can break the correlations of the data. So let's understand how this works. So for example, suppose this is a model that predicts insurance claims. And suppose features x0 corresponds to age, say this person's 21 years old, and feature x1 corresponds to driving experience, say this person has 4 years of driving experience. So when the x1 slot is empty, open source explainability methods like SHAP will compute the average model output by filling in fictitious values of x1 that it randomly draws from the data set. For example, for this 21-year-old, it might draw 3 other members from the data set to fill in this value of x1. And those 3 values might be 15 years of driving experience, or 7 years of driving experience, or 26 years. Because these are all randomly drawn from the data and not informed by the fact that this is a 21-year-old. So obviously these are unrealistic values for a 21-year-old. And said in a technical way, these values break the correlation satisfied by the actual data. And this is especially problematic if we're trying to explain an anomaly detection model that relies on subtle correlations to make its predictions. Okay, so we've just talked through one major drawback of open source explainability. We call that the fictitious data problem. And faculty has invested R&D into solving actually 3 shortcomings of open source explainability methods. The fictitious data problem is the first one. And there are actually additional problems relating to causality and human interpretability that we've also worked on. If you're interested, you can look up our papers to find out how we solve these problems. And I won't go into too much detail here, but let's talk for a minute about how we solve the fictitious data problem. We actually do it by augmenting the VAE that we use for anomaly detection with an additional component. The additional component is a masked encoder that operates on data with missing features. So the masked encoder operates on this input vector with x1 missing, and its goal is to extract a low dimensional representation of this data point that's similar to the one that the VAE extracts in the top row using all the features. This extracted representation can then be used to fill in values for the missing features that obey the correlations in the data. So instead of 15, 7, and 26 years of driving experience on the previous slide, this method leads to reasonable values like 3, 2, or 4 years of driving experience for the 21-year-old. And so said more technically, this method allows us to sample the missing features from the correct probability distribution, namely the one that's properly conditioned on the features that are not missing. And this is exactly what's needed to fix the fictitious data problem in open source explainability. Okay, so let me try to make this last point a little bit clearer with a demonstration of how all of this works on a simple synthetic data set. Okay, so we generated a very simple data set that's meant to represent, say, purchase histories for various individuals. So a typical individual has a purchase history that follows one of two common trends in this data set. In the left-hand plot, there's some natural noise in the data, but all the purchases hover around a value of 1. So let's call this left-hand individual a type 1 spender. In the middle plot, there's a little noise as well, but all the purchases hover around the value of 2. So let's call this person a type 2 spender. And type 1 and type 2 spenders make up 99% of this synthetic data set. The other 1% is made up by anomalies. And these are spenders whose habits shift at some point in their history. So in the right-hand plot, the final 5 features should be considered anomalous because they break the correlations that exist across 99% of the data. So across the majority of the data, each purchase that an individual makes is very correlated with their other purchases. They're either all type 1 or all type 2, give or take a little bit of noise. But these final 5 features sort of break that correlation in an individual's purchase history. So an explanation of this anomaly should recognize which features break the trends of the data. Okay, so this slide shows what happens if we just apply open source explainability to this simple data set. So there's a detected anomaly on the left, and its explanation is shown in the middle. And you can see from the plot that it's really hard to make out any useful information from this explanation. The 5 anomalous features are on the right, and they do have sizable Shapley values, but there are several other features that have Shapley values that are larger than some of the anomalous features. So this is just simply an incorrect explanation of the anomaly. The plot on the far right shows that the cause of failure here is the fictitious data problem. Let me explain what's going on in this plot. So to determine the importance of certain features, as we talked about a few slides ago, the open source Shapley calculation will remove these features and then fill them back in with random draws from the data set. So here I've showed the unremoved features in black. So the features that stay put, the features that we're not in this particular plot computing the Shapley values for. Those are in black, and the randomly drawn features to fill in the missing values are in coral. And you can see that what results here is a completely nonsensical purchase history that's really not representative of the data that we're working with. So this is the fictitious data problem. And in fact, this fictitious data point is even more anomalous than the true anomalies that exist in this data set. because the spending pattern here, if you take it at face value, just flip-flops numerous times between type 1 and type 2. And as we can see back in the middle plot, this leads to a really uncontrolled open source explanation with numerous errors. Okay, so this slide shows faculty's explanation for this anomaly. So notice that the anomalous features here in the middle plot receive Shapley values that are much larger than all the other features in the data, and no explanation errors are made in this case, and no close calls either. And the plot on the right shows that the fictitious data problem is solved using our VAE-based imputer. In this case, the coral dots correspond to the filled-in features. And you can see that this resulting data point is sensible and it's representative of what would be found in the data set. The only difference between the coral points that are filled in and what their original values were is just that random noise that exists in the data. Okay, so the last two slides showed explanations for a single example of an anomaly. This slide shows explanation accuracy averaged over the whole data set. And actually, it's explanation accuracy shown as a function of the noise that exists in the synthetic data. This noise is in reference, if I go back a couple slides real quick, to this natural noise in the data that's called out on the left here. So what you can see is that faculty's explanations maintain high accuracy in the high 90s over a wide range of natural noise levels that can exist in the data. However, the open source explanations become quite unreliable, dropping even below 50% as you go up in noise, meaning that the explanations are actually even more often incorrect than correct at the right-hand side of the plot. And so in the context of explainability for anomaly detection especially, this provides compelling evidence in favor of of faculty's approach that fixes the fictitious data problem. Okay, so that's all the material that I have, so I'll summarize quickly. So we saw at the beginning of the talk that explainability and robustness lie at the heart of faculty's AI safety program. Faculty's approach to anomaly detection results we saw in fewer false positives and more consistent performance than open source alternatives. We saw that the fictitious data problem in open source explainability leads to incorrect explanations, especially in the context of anomaly detection, where it's so important to get those correlations correct. And we've saw just now that faculty's approach to explainability solves the fictitious data problem and offers substantially more reliable explanations of anomalies. All right, so I guess I finished earlier than expected, so we have plenty of time for Q&A. I will start looking through some questions now and then going through some answers, hopefully. Actually, I'm having trouble opening. Having trouble opening the Q&A. So the Q&A is not opening for me. Maybe I'll stop sharing for a second, stop sharing my screen and see if that helps. Oh, I see, okay. Okay, so now I've got the questions open and I will look through them. Okay, so there's a question about whether autoencoders can be effectively used with types of data that are not images, as shown in the presentation. Um, so yes, definitely. Our variational autoencoder at faculty works very well in tabular data. So that's data where each feature follows a different distribution. So it's not an image, not necessarily text, but some of the features might be continuous, some of the features might be counts, some of the features might be categories. And so we handle those types of data very well. We've also got research projects going at the moment to work better on text. So variational autoencoders are really a broadly applicable tool that are useful for lots of different data types. But of course, there are other methods out there as well. There's a question about how you measure performance for unlabeled data. So that's a great question. Actually, before I answer that, or while I answer that, the reason that we set up this simple synthetic data set for the demo at the end is exactly for that reason, because it's difficult to measure performance for unlabeled data. So it's nice when we're benchmarking our method to have access to the ground truth. So in benchmarking data sets that will sort of tell you the answer after the fact, we do have ground truth for comparing methods against one another, but in real applications, you actually won't have the labels. You can't check your answers to see if you were right. And what's done in those cases is often, there's like a human in the loop, and the automated anomaly detection algorithm will sort of flag events in the data and pass those to the human investigator. And the domain expert will then look into the situation, hopefully aided by the explanation that was accompanied with the prediction, and determine whether this was a true prediction or a false prediction. And then once the human investigator does tell you the answer, this can sort of be fed back into model development, because then you'll eventually have a label that you can use to improve your model. Okay, there is a question about why I only presented results in terms of precision. So I put the word precision on the vertical axis just for simplicity, but actually what I was displaying there was the precision averaged over values of recall. That's actually the same as the area under the precision recall curve, which is a good measure of performance across like the full spectrum of model thresholds. And it's not possible to like hide a global disadvantage of an algorithm with the area under the precision recall curve. That's sort of sensitive to all values of precision and all values of recall. So that's what I was really showing there. There's a question, how many masked autoencoders do we need to train? Is it one per feature? And then this person is worried that because of the way the Shapley values work, we might need, a combinatorially large number of autoencoders to train. Actually, it's just one. So our masked autoencoder takes the full input vector as input, where this full input vector can have any number of missing features. And the way that works in practice is that we just sort of zero out the features that are missing, and also feed as input the mask. So the input to the masked encoder is the input features, where the missing values are just replaced with 0, concatenated with the mask so that the mask encoder can know, okay, if I see a 0 value, is that actually a 0 feature value or is that a missing value? So we just need to train one masked encoder and we can do all the combinatorics that we need to for the Shapley calculation. There's a question, how is your framework implemented? Can I plug into Python architecture with data in pandas and NumPy? Yep, no problem. We support pandas and NumPy data in Python. There's a question about whether we can please share resources about the data sets that we use in our benchmarking experiments. Sure, we'd be happy to. I think we can. I think we get a copy of these questions and we could email out responses. So we'd be happy to share information about the benchmarking experiments that we performed so that you can do your own comparisons if you're interested. Okay, there's a question about slide 35. What do I mean by accuracy of an explanation? So let's do that one. Okay, so accuracy of an explanation here is a reference back to these two explanations, the one on this slide, faculty's explanation, and the one on this slide, open source explanation. So in computing the accuracy of the explanations over the data set, I basically just made a choice here, and the choice was, I'll call this explanation accurate if the 5 largest Shapley values are the 5 rightmost features. So the ones that are truly anomalous in the data, do those features have the 5 largest Shapley values? That is true on this slide. So this would be counted as an accurate explanation. On the previous slide, that statement is false because the 5 rightmost Shapley values are not the 5 largest Shapley values. For example, like 1, 2, 3, 4, 5, there are at least 5 other values, 5 other Shapley values for non-anomalous features that are larger than one of the anomalous Shapley values. And the purpose of this final plot was to show that I didn't just cherry pick an example for you, like an example that came out really well for faculty and a really poorly for the open source method. That this is averaged over the full data set of like 10,000 points or something like that. And faculty's method is often giving correct explanations, 95+% of the time, whereas the open source method is causing errors a significant fraction of the time. All right, back to Q&A. There's a question about my thoughts on using clustering for anomaly detection. And there's a mention of Gower distance as sort of the distance metric to define the clusters. So I do have a couple thoughts on that. A few minutes ago, I was talking about how our variational autoencoder works well on tabular data. So tabular data might have some features which are continuous, take continuous values, some features which are binary, some features which are categorical, maybe some counts. You can just have all different types of data in a tabular data set. What the Gower distance would do is it would make some choices on how to compute the distance between 2 data points. And those choices, while they might be intuitive, they're somewhat arbitrary, right? Because if my data is age and driving experience and gender and income, for example, how am I supposed to compute the distance between two individuals that have like very different incomes, different genders, the same age, and different driving experiences? Is like 1 year of driving experience supposed to equate to like $10,000 of income? Or yeah, what's how do I get equivalent units on my axes? So the Gower distance does give you one natural way of doing that. But it is somewhat of an arbitrary choice. The advantage of the variational autoencoder is that the variational autoencoder takes this heterogeneous input and maps it into a homogeneous latent space. In latent space, so that's the like information bottleneck layer that I was explaining on the VAE slide. In latent space, all the features are continuous, and they all live on the same scale. So roughly an order 1 scale. And so we can take Euclidean distances in latent space, and that's one of the advantages of using a variational autoencoder instead of just like basic clustering with some arbitrary distance metric. There's a question about how much we need to alter the architecture of the VAE to be accurate for specific tasks. So on tabular data, which is what we operate on most of the time, but also for images, architecture tuning is always part of the process of training a VAE, but it's not prohibitive. So on tabular data, we might just use some fully connected layers and just try several different widths or sizes of the network, and just do a little bit of hyperparameter tuning for that width parameter. For image data, we'll use probably a convolutional architecture, and just hyperparameter tune over the hyperparameters of whatever architecture we choose. So yeah, we definitely have to tune architectures, but it's not a huge problem. There's a question, is our explainability library available as open source? Answer to that is no. So yeah, we try to sell that. There's a question about the causality approach. What would causality add to this? Would it explain why an anomaly occurred? Yeah, so I won't go into any details now. I can send you the paper after the talk on causality for causal explanations. What causality will basically let you do, though, is if you have some domain knowledge of like which features are causally upstream and which causally downstream, what comes first, what comes second, it will let you simplify explanations. For example, if two features are deterministically related to one another, a regular Shapley approach would just give them the exact same Shapley value. And so if you have many features that are highly correlated with one another, regular Shapley would just give all of those features equal or roughly equal Shapley values. If you inject some causal knowledge, you can say, no, I don't want this like uniform explanation. I'd prefer to put all the explanation on the first root cause, the causal ancestor of this process. And so it can simplify explanations and make them more intuitive and more in line with the causal basis for the data generating process. But I'll point you to our paper for more information on that. Okay, there's a question about, oh, good point. So there's a question about the last part of the talk, how I showed the accuracy of faculty's approach compared to open source alternatives. And the question is, am I like pulling a fast one on you guys by using accuracy here instead of precision and recall? So the answer is no, but it's a good question because I didn't explain this. So this is explanation accuracy restricted to the anomalies only. So this data set that I've set up is actually like super simple. It's quite easy for any anomaly detection method to detect these anomalies with perfect precision, perfect recall, perfect accuracy. So the accuracy of the performance of the anomaly detection method is not what we're trying to measure here. We're just trying to focus on the correctness of explanations. So what I've shown in this final plot is just the explanation accuracy on the anomalies. So if the data contained 1% anomalies, it's just the explanation accuracy on those 1% of anomalies. So this is, I think this is the metric that you would want to see. You can imagine if these 1% anomalies were then passed to like a human team of investigators here, and they were accompanied with their explanations, 100 or 95 or 90% of those explanations would be correct using faculty's method, and much fewer would be correct using the open source method. That's what this says. So there's a question about, going back and explaining the coral and black dots here. Yes. So the coral and black dots here are supposed to be the same thing as, if I go back a few slides, the same thing as basically this black feature and this coral feature. So the black feature is the original value that the feature takes in the data point that I'm trying to explain. And then the coral feature is a feature that I'm trying to get the Shapley value for. And the way I get the Shapley value is I remove that feature and I see what effect this has on the model output. But of course, I can't just leave the model's input feature slot empty. I have to fill something in. So I fill it in with this coral value. And the coral value that I fill it in with is drawn from the data set in the open source technique. So it might be drawn from some other random data point. It might be 15 years, for example, that we plug in on this particular calculation. So now going forward again. So the black data points are the data points from the original data point. Like if you try to check them from far left plot to far right plot, they should match. And then the ones that are missing in black are then filled in coral by splicing in another data point from the data set. And this other data point that happened to be spliced in was actually a type 1 spender. And you can see that if you splice together a type 2 spender and a type 1 spender, you get a pretty nonsensical data point. Plugging this into the model then is just going to lead to a very confusing explanation because the model has never seen any data like this. And in fact, this is a like extreme anomaly. And so the model is going to behave in an extreme way. And that's what leads to this confusing explanation. Whereas on this slide, so same black points, these are the original feature values. And then the coral points now are filled in by faculty's VAE-based data imputation method. And so you can see that these are filled into reasonable values that represent the type 1, type 2 spending, type 1 versus type 2 spending that's common in the data, and also the noise that is characteristic of the data. So somebody asked if I could explain a little bit more faculty's approach for solving the fictitious data problem. Is it correct that an additional autoencoder is trained to generate likely possible values for the missing features. Yep, that's pretty much correct, except maybe not the word additional. So if you're already doing anomaly detection, say with a VAE, then you've already trained this anomaly detector up top, this VAE. If you also want to explain your anomaly detection, you have to add a component to your VAE, this masked encoder down here. And you're right that the basic task that this masked encoder performs is encoding a data point with missing features into this information bottleneck, this latent space, so that it can be decoded and come out with reasonable feature values. So it's a way to sample. It's a way to sample missing feature values from the conditional distribution, conditioned on the true values of x0 and x2. So that's why x1 comes out sampled with reasonable values like 3, 2, and 4. But yeah, so the way we solve the fictitious data problem is when we fill in missing feature values, instead of just drawing them from the data set, we use this VAE-based data imputer instead. That's also a reason why this wouldn't work so well, maybe as an open source approach, because it requires some familiarity with training VAEs on different data types and using VAEs in the Shapley calculation process. But there's a lot of like machine learning expertise that goes into getting a good VAE trained on a complicated data set. And also, this isn't just a VAE. This is this VAE plus masked encoder. So it's even more of a specialty, I guess. Okay, there's a question if the slides will be available after the talk. Yes, the answer to that is yes, and I think a recording will as well. All right, but it's been an hour now. There are still plenty of open questions, but I think we can email the people that ask the questions with answers. So I will keep looking through questions and email answers, but maybe I'll turn off the webinar now. So thanks everybody for coming. Oops. Thanks everybody for coming. Hope you enjoyed it. Hope you learned something. And yeah, if you're interested in working with us, or if anomaly detection or explainability are important for your business, don't hesitate to reach out to us. We'd love to talk to you. All right, thank you.